Welcome everyone, this is Computer Vision lecture number 7. Today I'm going to introduce you to artificial neural networks. Before we start, just a quick reminder, next week there'll be our first quiz, so that'll be December 8th. The second quiz will be in the next year, in February, and both will be purely online. We'll be testing this functionality in the whiteboard on, I think, next Thursday. Each of these quizzes will be 45 minutes, and both quizzes contribute equally to the final grade. So the points that you earn in quiz number 1 will be added on top of the points that you will earn in quiz number 2, and together with the bonus points that you can earn on the assignments, your grade will be a function of this total sum. So make sure you go and register for those quizzes. Otherwise, we won't be able to let you attend these. So we now finally switched over to the deep learning part of computer vision. So this lecture kind of introduces you to even older concepts as some of those papers that we discussed before, but we'll gradually move into more modern architectures and methods. So let's start by looking at that picture. What do you see on that? So, you might say, okay, that's a dog, or that's a hand holding a flower, or there's some grass in there. And I just wanted to make the point that our brain takes in this very complex input, right? So this is not just a dog, it's a specific type of dog, and it's looking in a very particular way. So what our brain is doing is that it takes in this complex input, and it decomposes this image into a hierarchy of different structures, right? So we can localize and identify objects like the hand and the flower and the dog, but also these objects, for themselves, consist of different objects, like the ear and the nose and the eye of the dog. And even then, these things again consist of different patterns, like they have like texture, and they have some color gradients, or even like some shapes, and these again consist of low-level patterns, and these low-level patterns eventually go back to pixel structures or pixels. In computer vision now, we basically want to do the same process but in reverse. So from pixels we want to detect lower-level patterns, high-level patterns, and we want to construct object parts from these, and then from the object parts we want to construct objects. So in the end we have the notion about where is the hand in the image, and where is the flower, and is there a dog or not. And in the following lectures we'll always use artificial neural networks, and these are universal function approximators. So whatever input we have and whatever output we want to have, we can just collect samples that, for example, here show dogs and flowers, for example, and outputs, for example, here like labels that we want to be able to get from that function. And then we collect many of those input-output samples, and in the end we want to train that network, which basically means we want to optimize all its parameters such that the error is minimal. And that's what we do in machine learning, and that's what we will do throughout the whole lecture. So that's pretty different from what we have been doing in the last couple of lectures, because there the features that are relevant and the way they are connected to then form an estimation or a prediction about whether there is some object in an image, or to predict the location of the object in the image. These these rules were like handcrafted, and now we want to learn these given a set of input and output samples. And we will see that neural networks now learn to represent this hierarchy of low-level and mid-level features up till the point where we have output neurons that represent the existence of objects, for example, that ANNs learn to represent these features in the layers that they consist of. So to understand how ANNs process inputs to outputs, we need to understand what these single units here in yellow, what these things do. So an artificial neuron now collects inputs x1 through xn and individual weights wi through n into a sum, but we also add a parameter that we call b for bias. Now this entire sum is then pushed through a so-called activation function, and that is a nonlinear function. This time here we use the sigmoid function, the logistic function given by that equation here, to squash the input from like a wide range of possible values into values between 0 and 1. Now, look at what we do here. You probably have seen that, and you should be able to say what we do here. Exactly, that is the dot product. And remember what that does exactly. It matches the input x to a certain pattern w. So think of our data to be either stars or orange triangles. And imagine we have already learned weight vector w, and now multiplying w with x, here in w transpose x, results in a number, in a scalar number, that is positive if those vectors x are in the positive half space, or this positive subspace, so everything left of that line here. And it's negative if those vectors are in the opposite side of the world. And b now can be tuned, right? It's another parameter to, subtract something here, essentially shifting this decision boundary up towards w, so that some samples that previously have been lying in this positive subspace are now in the negative subspace, right? So we can optimize w and b to create a decision boundary such that all those stars and all those triangles are optimally separated. And we call this logistic regression. For those of you who don't know what that is, look in the link. So look in the description. I'll post a link for you to watch another video. So ANNs now consist of multiple layers of these units, and we call them also features because they are detecting patterns in the input, right? So each of these units here connect to all those input variables, and after training they have a specific set of weights that detect specific patterns in the input. And so high output values for this unit then mean, hey, there's this pattern that I detected. Now, obviously you have different features with different weights and therefore different patterns that each of these units detect. Now, since we have multiple layers now that receive input from the previous layers, ANNs basically have features that detect patterns in previous features. Yeah, so for example, think of these early things as like maybe corners or differently oriented edges, and then we can combine these in a certain pattern in a different combination of weights to, for example, detect like corners or other geometrical structures. And since we have many of these layers, these can become increasingly complex. And in the final layer, we usually encode, in classification tasks, the probability of objects in the input. So for example, one of these units encodes the probability of the input containing a hand, and the other unit contains the probability of the input containing a flower, and so on. Now, these features here can be reused, right? So some of these patterns may play a role in each of these output in these objects, right? So for example, certain gradients or corners are important in the existence of a hand and flower and dog, but the specific weight for them in the pattern that these units look for may vary. So it's straightforward to calculate the output of an ANN. So given an input vector x with its individual inputs xi, 1 through n, we introduce a weight matrix, so connecting all the inputs and the additional one to all the intermediate features. And you can imagine this W1 bar to consist of a weight matrix that is only responsible for connecting the inputs x1 through n to the intermediate features. So that's the W without the bar, and adding one column of parameters who here correspond to those biases. So W1 bar times X bar enters the sigmoid function, so that's the activation function for this layer, and that produces an output Y1 hat. Okay? So X with this bar here is only the extended, the concatenated vector X with the additional one displayed here. And so those dimensions match that this can be multiplied. Now for the second step in this two-layer network, we'll use the same notation as described before. So given a certain configuration of weights and biases, we can easily calculate an output given an input. But that doesn't make any sense because we haven't yet talked about how can we optimize those parameters to minimize the overall error over a given data set. Learning always means let's find the best set of parameters, and those parameters are here visualized by those knobs on this mixing device. And for you, that oftentimes, as a practitioner, oftentimes means calling one function, right? So given a set of training images and respective training labels, we just call that function fit. So we optimize those parameters to optimally represent input and output. Now, how does that work?